But initially, it's real key that we do problems that are the same degree of difficulty as what you've been working with. And at this point, I don't know what that is. How about, do you have your test that you got back?
I can keep the answers I put down, but the actual test he keeps.
Do we have, so we don't have the problems?
Yeah. I could actually find my online.
That'd be the best thing, is if we could review that test and go over the ones that you missed.
Yeah. Oh, wait, he made us actually do some problems, and let me find those. Sorry, I'm just trying to get organized here.
Okay. Actually, no, I need to get my other trick book, because it has some of the sum to difference and difference to sums. All right.
I'm not working. Let me just check my website then.
I mean, I got access to plenty of problems, but I don't know that they're the appropriate ones for you.
Yeah, that's a good point.
Because these things come in all kinds of flavors of difficulty. I mean,
Let's see, 4.7. Okay, this book is an older version. It doesn't always match up. Okay, let's just use the problems within this thing.
okay.
I'm going to do it this way. So let's see the answer. In fact, let me find the practice problem instead.
Okay.
There we go, so I don't have to look at the answer later. So how about this? Cosine parentheses pi over 2 plus pi over 6.
Plus what?
Pi over 6.
Okay. And we want to use the sum and difference formula, or identity. So let's write the sum and difference at the top here. What is the cosine of A plus or minus B? Does he make you memorize these, or does he give you these on the test?
Memorize these.
Okay. So the reason we start with cosine and not sine is it makes it easier to memorize. Cosine is cosine, cosine, minus or plus, sine, sine.
Yeah.
That's all you need to memorize, because the letters will fill themselves in. In other words, I know that the sum and difference answer has 2 cosines and 2 sines in it. I also know that the sine is opposite for the cosine sum and difference. And I know that it's cos, cos, minus or plus, sine, sine. So, remembering what it is, well, it must be cos A, cos B, and minus or plus sine A, sine B. So that's kind of the way I memorize it. And then sine of A plus or minus B, it's got the same number. It's got 2 coses and 2 sines in it. But instead of this, it's alternating. So it's sine, cosine, same sign, plus or minus, not minus or plus, sine, cosine. And in the letters, they are always different. In other words, that's an A and that's a B, and that's a B and that's an A. So that's the way I memorize those two. So how do I apply it for the cosine of pi over 2 plus pi over 6?
Well, you need to find the sine and cosine of both of those.
Okay, so first of all, let's write it out. So it's the cosine of what?
Cosine of pi over 2 times the cosine of pi over 6 minus or plus.
No, just minus, because we've got a plus there, so it's just minus. In other words, when I use plus and minus here, it means that covers two different situations. And the sign over here is always opposite for the cosine one. Cam, I'm going to turn my camera off because my computer is complaining about my speed usage here. Shouldn't make any difference. So the rest of this is what?
It's sine pi over 2, sine pi over 6.
Okay, now let's fill in numbers for this. What's cosine pi over 2 equal to?
I have to check the unit circle. Pi over 2 is
now is that something?
Degrees, right?
Right. And that's something else that you should have memorized, I imagine.
Yeah.
And the way to memorize that is to memorize what the graph looks like. There's the cosine graph. And remember that it's always 2 pi and that this thing breaks up into quarters. There's a pi there. That's always pi over 2. This is always 3 pi over 2. So now, when you're trying to remember what the cosine of pi over 2 is, I wouldn't think of that unit circle. I would think of this, because you need to have this memorized anyway. Since you have to have this memorized anyway, you can just recall from memory that cosine starts at 1 and goes down to 0 next. So cosine of pi over 2 is 0, which makes this whole term 0. Regardless of what cosine of pi over 6 is, I don't care. Okay, and what's the sine of pi over 2?
The sine of pi over 2 is 1.
Again, coming from this curve, sine starts at 0, goes up to its maximum, comes back to 0, goes down to its minimum, and comes back to 0. And so these quarter points are going to be pi over 2, pi, 3 pi over 2, and 2 pi. Okay, and what's the sine of pi over 6? Again, you don't need that unit circle to be memorized. You need to be able to know that pi over 6 is the same as 30 degrees. And then go to your triangle, your 30-60 triangle. And what's the sine of 30 degrees?
The sine of 30 degrees, let's see, opposite of hypotenuse, so 1/2.
Okay. That's the way I think a person should do it. This memorizing the 16 spots on the unit circle, I guess before I criticize it, I should say, have you done it? Have you been able to do it?
I've memorized the first part of the unit circle.
First quadrant?
Yeah, and then I can just use
well, that's a good start. Yeah, that's all that you really need to memorize is that first quadrant, but you also need to memorize the quadrantals. The pi over 2, the pi, the 3 pi over 2. In other words, the multiples of 90 degrees. And to memorize the quadrantals, you really need these two graphs, I think.
Yeah, those ones are easy. Those ones are easy for me.
Okay.
Yeah.
So you don't really need those triangles anymore. You've got those trig functions memorized. So the answer to this then is minus 1/2. And that's the cosine of pi over 2 plus pi over 6. That has to be second quadrant. So we know that that's got to be negative. So that makes sense that it's minus 1/2. It's always a good idea to do a bit of a ballpark check to make sure that cosine of an angle greater than 90 degrees is indeed negative.
That is outside the first quadrant?
What's that?
That is outside the first quadrant?
Still didn't quite hear what you're saying, Cam.
It looks like, never mind.
Okay.
No.
Okay, I'm going to erase these two here. You have another one?
Yeah, I can get another one.
They're pretty much plug and solve. In other
Yeah.
words, if you can memorize these two, that's the only problem.
Now we have cosine 7 pi over 12.
Okay, now it gets a little bit harder because it's going to force us to break this up. And we got lots of choices as to how to break that up. Now, let me make a suggestion. If you're not yet comfortable thinking in radians, then turn it into degrees and figure out how to break that up.
Yeah.
I'm comfortable enough that I recognize this. That's 3 pi over 12 plus 4 pi over 12.
Oh,
Okay, let me just write that, and you'll see why I remember that is because 3 pi over 12 is pi over 4, and 4 pi over 12 is pi over 3. So I'm going to be able to use my A and B are going to be pi over 4 and pi over 3, and I know the cosine and sine of those angles. However, let's go through the conversion. Convert this to degrees for me.
let's see.
What's the conversion factor?
Times 1 to 80?
Over
180.
180 over pi. Remember, that's our conversion factor when we're going radians to degrees. It's pi over 180 when we're going degrees to radians. But there are 180 degrees per pi radian, or there is 1 pi radian for 180 degrees. So when we convert this to degrees, notice the radians fall away and we end up with degrees. 12 goes into 180 15 times. 15 times 7. There's our degrees. Now, with it in degrees, it's a little easier to figure out how to split it up. If I gave you this problem with, instead of 7 pi over 12, I said, let's figure out the cosine of 105 degrees, you'd be able to split that up into 45 and 60.
Yeah.
So it's really... What's that?
It was a lot easier for me to see that in degrees, so I wouldn't
Well, I would use that as your game plan then, is that whenever they give you radian measurement, convert it to degrees, do the problem, and then you may or may not have to convert back to radians. In this case, we're not going to have to ever convert back to radians because everything becomes numbers. Whether we put in 45 degrees and 60 degrees or pi over 4 and pi over 3, we're going to plug it into this formula, and we're going to come up with numbers. So let's do it.
Okay, so we have cosine of 60 degrees.
So we're going to do cosine plus 60 plus 45, right?
Uh-huh.
Okay, so we got cosine of 60.
And sine 45.
Hold on. Cosine of 60, cosine of 45.
Sorry, plus
No.
sine of...
The
Oh,
sine,
minus.
for the cosine one, it's opposite. Whatever this sign is going to be opposite. In other words, if this started out as a minus, this would be plus. For the sine, it's the same. In In other words, if we're doing the sine sum and difference, notice that it's plus minus plus minus. But for the cosine, it's opposite. So in this case, it's negative. And then sine of 60, sine of 45. What's cosine of 60?
Cosine of 60 and maybe the 1 over 2.
Okay. I tell you where I start with my memorization is this one right here. If this is true, then cosine of 60 has to be the same thing, because the sine of an angle is always equal to the cosine of pi over 2 minus that, or of 90 degrees minus that. So the sine of 30 is the same as the cosine of 60. The sine of 31 is the same as the cosine of 59.
Yeah, I haven't looked at the first quadrant in a little bit.
Well, it's good to recognize that this angle 60 is complementary to the 30.
Yeah.
And whatever is complementary is the same number. So if I've memorized the sine of 30 is 1/2, then I've also memorized the cosine of 60 is 1/2.
Yeah.
Cosine of 45?
Root 2 over 2.
Sine of 60?
Root 3 over 2. Root 2 over 2.
So what we end up with is square root of 2 minus square root of 6 times 1/2. Times 1/4.
Yeah.
And that is also a negative number, because square root of 6 is bigger than square root of 2. And it should be negative, because once again, we're in the second quadrant.
Yeah.
And you can give a number for this, although if you're taking a multiple choice test, this is liable to be your answer. Your answer is going to look like this. Probably not a decimal number, because this is the most accurate answer you can give. Okay. What else? I think you got the sum and difference down now, right?
Yeah.
Okay. What if the trick on the sum and difference isn't so much remembering these two, it's how to separate an angle. So let me give you some practice. What if I was doing 165 degrees? How could I break that up?
Let's see. We could 90. No, that wouldn't work.
Now remember, you can break it up by causing it to be the sum of two different things, or you can break it up by causing it to be the difference of two different things.
You could have 120 degrees plus 45 degrees.
Good. We know what 120 and we know what 45 are, and that's the key. You always want to break it up into two angles that you know you can figure it out without a calculator.
Yeah.
And 120 is 1. Okay. Another way. What's another way we could break it up?
Um.
How about 210 minus 45?
Oh yeah.
That's the only two I can think of at the moment. Obviously, we could extend this to 265 minus 90, or 255. No, we don't know 255, so that wouldn't help. Wouldn't want to do that. In other words, you got to always break it up so that you end up with angles that we know without a calculator.
Yeah.
That's going to be the goal when you take a test, is because this is going to be a non-calculator point of the test. because their whole point here will be to get you to break up these numbers into either the sum of two numbers or the difference of two numbers. Okay, how about, let me just give you one more there, and then let's go on to a different subject.
45 minus 30 degrees.
All right. All right. I think you got the hang of it.
Yeah.
In other words, this is the tough part. And once you get this, you just have to remember these two formulas and plug in and solve.
Yeah.
All right. What else do you want to go over?
This one looks interesting. Cosine 7 pi over, no wait, did we just do that one?
7 pi over 12? Yeah, we did that.
Sine negative 5 pi over 12. My bad, we just did the final.
Sine of negative 5 pi over 12.
Yeah.
Well, we can approach this two ways. We can convert it to degrees and see if we can figure out what subtracts to that. That's 75 degrees, so let's do it that way. Sine of minus 75 degrees. Now we got two ways to go. We know that that's the same as minus sine of 75 because it's an odd function. The sine of minus theta is always equal to minus sine of theta. And now that's minus sine of 30 plus 45. Okay? So you can see how we would proceed that way.
Mm-hmm.
Let's go back and see if we can do it without using that piece of information. Well, we probably can. How can we break up two numbers so that we end up with a negative 75?
Let's see what we do.
Well, think of a combination that involves subtraction where you would subtract a 75.
45 minus 120.
Well, we don't know what'd you say, 145? But we don't know
45 minus 120.
Minus what? 1?
20?
There you go.
Yeah.
That's all you need to do. In other words, we don't have to know that the sine of negative theta equals negative sine of theta. We can just figure up our two angles that give you a minus 75 and then plug these into the sine sum and difference formula. Most important part about these really is kind of keeping your signs straight, your plus and minus signs.
Mm-hmm.
Because it's easy to get them off. You got a lot of negative signs and then negative results. So, okay. You need to go further on this, or are we good on this problem?
Yeah, I think we're good.
Okay. We can take it as far as you feel a need to. I feel it makes more sense for us to set them up than to actually come up with the answer. Because presumably once you get it this far, you're home free, right?
Right, it has kind of an interesting answer, so I'd like to just look at it.
Do you have the answer on this?
I could check the answer. I know the answer to the normal problem, but and I know the normal problem is interesting. I usually have a similar answer.
Okay, because we can take this to fruition if you feel a need.
Yeah, let's just try it out.
Okay, so what do we got? What are we gonna right here. It's equal to
So we're
what?
going to use sine 45 times cosine negative 120.
No.
No, cosine 120, my bad.
There you go. In other words, don't put the negative sign with that. We're doing a subtraction formula
Yeah.
here.
Minus
There you go.
the sine of 120 times the cosine of 45.
Right. And always remember this angle is different than this. In other words, it's not sine of 45 cosine of 45. It's sine of 45 cosine of 120. Because one thing, when I went to memorize this once, I realized that I wasn't positive whether this should be A and this should be B, or it's correct this way. And so I realized that these always have to be different letters here. In the first case, with the cosine one, it's obvious that they would have to be different letters.
Yeah.
But not so obvious for the sine case. Okay, so now what's this? Plug in numbers here.
So we have root 2 over 2 times root 3 over 2 equals 1.
Positive or negative?
Is it a negative? It's also
Cosine is negative in the second quadrant. All students take calculus. In other words, rather than remembering a unit circle, you just want to remember these bits of 4 pieces of information at a time. In other words, that's the same as the cosine of 60, right?
Mm-hmm.
Only it's negative. Cosine of 60 is 1/2, so this is negative 1/2. And then minus
root 3 over 2.
and that's positive because sine is positive in the second quadrant.
Mm-hmm. And root 2 over 2.
So this answer is negative root 2 over 4 minus root 6 over 4, or negative root 2 minus root 6 over 4.
Okay. Let me tell you the answer they got. It is negative 1/2 root 2 plus root 3. As in, it's all the root 3 is within the roots of root 3.
Ah. So they didn't give the answer like this. What answer did they give?
Let me show you. It's negative 1/2 root 2 plus root 3, except the root 3 is also underneath the same bracket root 2 is under. I mean the same root.
Oh, like this.
Yeah.
Interesting. Well, there's no doubt in my mind it's the same number, but I've never seen an answer like that. It reminds me of Bombelli's complex numbers. If I ever showed you this, that 4, Bombelli lived in 1572, and he discovered that 4 is equal to the cube root of 2 plus the square root of negative 121 plus the cube root of 2 minus the square root of minus 121. The number 4 is equal to that, which is pretty strange given that we have complex numbers involved here. In other words, this is I, 11i, so we're taking the cube root of 2 plus 11i plus the cube root of 2 minus 11i, and that's equal to 4. But that's the only other time I've ever seen the radical inside of a radical, which is the way you just presented that answer.
Yep. That's
Seems to
good.
me that it makes much more sense to present it like this. Whoops. Doesn't it to you?
It does.
Rather than a radical inside a radical. Wow, that is radical.
I have to look up what kind of answers they were giving us that I was just confused.
That's why you said that was a peculiar answer. You were right. Okay. What else you want to go over?
Let me find a different one this time.
You mentioned at the start that you were doing sum to product and product to sum also? Or not? Most of my trig students, some of them get into product to sum and sum to product, and others don't. So I don't know.
I haven't heard too much about it.
Okay. And then you probably haven't gotten into it. And we don't want to get into it if you haven't, because it's a different. Have you done double angle or half angle yet?
I'm trying to find a double angle in here. And I know we've been doing them.
Okay. I can bring some to the table on that. Are these identities that you have to memorize also?
Yeah, sometimes he writes them on the board, but I think memorize them. It's just kind of forgotten.
Okay, can you do this one from memory? This is a pretty easy one to memorize. That's 2 sine theta cosine theta.
Okay.
The tough one is the cosine of 2 theta, and this is probably what he might write on the board, because there's 3 of these. And there's a reason there's 3 of them. I'll explain it in a moment. The reason we have 3 different identities for the cosine of 2 theta is because sometimes you're solving a trig equation and you want everything to be in sine, so you would use this one. Sometimes you want everything to be in cosine, so you would use this one. And sometimes you want everything to be a combination in cosine squared and sine squared. What do I mean? Where could this pop up? Let's take this problem right here. If I were to go to try to solve this equation that I've written down here at the bottom, which trig identity would I use? Remember the way I'm going to solve this. Think back to have you had solving trig equations?
This is just the area I've never really been good at.
Okay. The way we're going to solve this is by treating it as a quadratic. Now, if I'm going to treat this as a quadratic, the identity I want to use is this one right here, because then it allows me to write it like this. 2 cosine squared theta minus cosine theta minus 1, here's the minus 1, equals 0. Now I can factor it just like it was a quadratic and solve it. But notice that I had to get it entirely in cosine. If I would have used this identity, I would have had a combination of sine squared and cosine theta. And then I would have had to keep substituting to get it everything into cosine theta. And occasionally you want to use this one if the equation warrants it. But in a simple equation like this, I'm always going to pick the identity that has nothing but cosine squared in it, because I know I can solve that quadratic.
Okay.
Okay? So that's why we have three different identities for cosine. And I don't know, I'm guessing he won't make you memorize all three of them. Those are the ones he might put up on the board. But do you have any questions as to how we use these? In other words, let's say I wanted to figure out the sine of, let me think for a second. Oddly enough, when you use the double angle, let's say we want to figure out the sine of 60 degrees, and we don't know what it is. So we're going to say that's the same as the sine of 2 times 30. So now theta is 30. You with me?
Mm-hmm.
So that's going to be 2 sine of 30 cosine of 30. Of 30 rather. Which is 2 times 1/2 times root 3 over 2. That 2 cancels with that, and I end up with root 3 over 2, which I knew to be the correct answer anyway. Now, if you went through the process that I just went through, trying to find an angle where we would have to use the double angle, it's hard to do that, because everything that we know theta to be, all of those angles, well, 2 times theta, we know what those are already. In other words, if theta is 30, I know what 60 is. If theta is 45, I know what 90 is. So I don't need to use the double angle to solve trig problems.
Yeah.
Half angles, different story. The reason we have a double angle identity is for solving trig equations, not for solving particular angles. In other words, there's no angle theta that I happen to know that I don't know the 2 theta for. So I don't ever need to use this unless I'm solving a trig equation. Half angles are a different story. Let's just look at one half angle formula.
Okay. No.
This is the square root of 1 minus cosine of 2 theta all over 2. Whoops, hold on. Sorry, I'm writing the wrong one. Double angle and half angle. Here we go. Sine is 1 minus cosine of theta, not 2 theta, all over 2. So this can be helpful finding trig functions of some angles that we don't know. In other words, if I wanted the sine of 22.5 degrees, what's that going to be equal to?
So that would be root 1 minus cosine 22.5 over 2.
Well, let's write it step by step because it's easier to see. Sine of
Okay.
22.5 is the same as the sine of 45 over 2. So when we write it like this, we see that theta is 45. So now we're going to substitute 45 for theta. So it's 1 minus the cosine of 45 over 2. In other words, this gives us a way to solve for half of any angle. Well, that covers a lot of angles. I could solve for the sine of 15 degrees because I know 30. I can solve for 22.5 degrees because I know 45. I could solve for 75 degrees because I know 150. So see the way we can use the half angle identity. We can use it to find angles that we had no way of finding before. The double angle identity, not so much. I could not find an angle that I needed the double angle identity to solve. We need the double angle identity, but only for solving trig equations, not for solving trig functions of weird angles. However, the half angle identity can be used to solve both trig equations and trig angles of weird angles, trig functions of weird angles.
All right.
So that's the double and the half. And it's a similar problem as we have sum and difference, is that the secret becomes figuring out what theta needs to be in order to, in other words, let me give you some tests. What would the sine of 15 degrees be, and rewrite it as a half angle?
Okay, so we have sine 30 over 2.
Okay.
And if that equals to root 1 minus cosine 30 over 2?
No, cosine of 30, all divided by 2.
Yes.
In other words, theta is 30, not 15.
Mm-hmm.
Okay. And we know that's square root of 3 over 2. Ah, now I know why they gave you the answer like that. Notice what happens here. 1 minus square root of 3 over 2. See how I end up with the radical sign inside the radical sign?
Yeah.
In other words, I still have to make this 2 over 2, and then I still get rid of the 2's. Oops, no I don't. They become 4's when I divide by this. So now I end up with the square root of 2 minus radical 3 all over 2. That's what they did on that other one. It's almost like they used the half angle formula to solve that other one.
Yeah, I'm guessing they did.
Yeah.
Yeah.
And that's how you end up with a radical inside a radical. Yeah, interesting. I'll bet you anything that's how they solved it. Now the other one, we had 2 ways to do it. I erased it all. But it must have been a half angle solution type problem also. Okay, we got about 12 minutes. What subject matter would you like to cover? Is there anything we haven't covered that you wanted to cover?
Let's take a look. Let me see if there's anything from the next section as well.
Okay.
About the arc sine functionality. Yeah.
Okay. Arc, inverse tangent, or inverse trig functions, are you comfortable with those? Let me give you some.
Not really.
Okay. Here, let me explain the principle here. If the sine of an angle, remember we are always taking trig functions of angles, that's equal to a number. This is the angle, this is the number. Forget radians for a moment. Let's keep angles in degrees, numbers as numbers. That is only true if the inverse sine of the number equals the angle.
Yeah.
This is an if and only if. Sine of 30 equals 1/2 if and only if the inverse sine of 1/2 equals 30. So just remember you have to reverse the range and the domain.
Oh, these are
We take inverse trig functions of numbers to get angles.
Yeah.
So let me give you a few that you should know.
Yeah, I remember. I was looking at the graphs. And I was just
What's the inverse cosine of that equal to?
that would be That would be 60 degrees.
No, remember cosine of 60 is 1/2. So that's 30 degrees.
30.
What's the inverse tangent of 1 equal to?
No, that's a quartile.
What angle does the tangent of that angle equal to 1? That's what you want to ask yourself. Where is the tangent equal to 1? What angle?
That's one I don't know. I'm not too good at the tangents.
Okay, well, let's go back and look at our 45.
It must be a 45.
45 degrees.
Yeah.
The tangent's equal to 1 at 45 degrees.
Yeah.
Okay. Where is the inverse sine of root 2 over 2?
That would be 45 degrees.
What's the inverse sine of negative root 2 over 2?
That could be two answers, couldn't it?
Actually, all of these could be. The calculator will only give you the principal value, which is defined for sine as being first and fourth quadrant, and tangent as being first and fourth quadrant. So the answer they're looking for is the fourth quadrant answer, not the third quadrant answer. Unless, of course, they say that theta is greater than or equal to 0 and less than 2 pi, in which case they want both of them. But if you put this into your calculator, the inverse sine of negative root 2 over 2, it will give you only the fourth quadrant answer.
Okay,
So what's the fourth quadrant angle for 45 degrees?
That'd be 315 degrees?
Or another way to do this would be to take that negative sign and say it's the same as minus inverse sine of root 2 over 2 because it's an even function. So, or minus 45 degrees. Either that or that is correct. Although if it's a multiple choice test, I'm guessing this is what you'd be looking at, the minus 45.
Yeah.
Okay, before we leave that topic, let's look at the cosine. If I said, what's the cosine, inverse cosine of minus 1/2? Without this restriction. In other words, you're going to get this off your calculator. Which quadrant are they talking about? What are the primary quadrants for cosine? For inverse cosine, excuse me.
Would it be the second quadrant?
First and second. In other words, all positives are going to be first quadrant answers. All negatives are going to be second quadrant answers. So what is this?
Negative 1/2. Let's see. 120.
Exactly. In other words, we're looking for that 60-degree angle in the second quadrant, which is the same as a 120-degree angle. Now, if the problem said this, theta is in the unit circle, what's the other answer besides 120?
Let's see. This is the third quadrant.
Okay.
So that would be, won't be 180.
Okay, let me give you a good way to do this. Right. In other words, we're solving this equation. We're trying to find an angle such that 180 minus, excuse me, I got these backwards. I hate it when I do that. This one's 180 minus theta. This one's theta minus 180. So we know that our first quadrant angle is 60, right? So the solution to that has to be 60. In other words, theta minus 180 has to equal 60. And if I solve that for theta, I get 240. So 240 is the second solution. And it's perfectly true if you look up your calculator, the cosine, inverse cosine, or if you look up the cosine of 120, you'll get negative 1/2. And if you look up the cosine of 240, you'll get negative 1/2. But if you look up the inverse cosine of negative 1/2, you will only get that answer, because they only give you the primary quadrant. And for cosine, the primary quadrants are 1 and 2. For sine and tangent, they're 1 and 4. Okay. So that's all there is about inverse. There's really nothing magical about inverse at all. It happens to graphically be the same as you would expect all inverse functions. In other words, if I want to graph the inverse sine, I start with the sine, I run a line y equal x, and I take, actually on inverse sine, I restrict the domain from minus pi over 2 to pi over 2, because that's the only way the sine function is 1 to 1, is on that restricted domain. So now, to see what the inverse looks like, I merely reflect the sine curve about that line, and it ends up looking like this. I'll try to draw it with a dotted line. Something like that. So the inverse function looks like that dotted line there. But remember, inverse functions merely reverse the range and the domain. So when I say the sine of 30 degrees is 1/2, the inverse merely reverses those two numbers. And only when I restrict it from minus pi over 2 to pi over 2 is it a function. It still passes the vertical line test. Whereas if I flip the whole sine curve over the axis, it would look like this. Well, no, it would come back in on itself, and it wouldn't pass the vertical line test anymore.
All right.
Got time for maybe one more question or problem?
So that was everything covering the two sections of the quiz.
Okay. And you have to, he's going to let you retake that quiz, or everybody retake it?
Well, we're going to have a test next week, so I just wanted to...
covers that same material, yeah.
Yeah.
Well, Cameron, I would really advise you to review this session, because I think we've talked about everything you're going to need to memorize and the methods that you're going to use to answer all these questions. So if ever you review a session, a tutoring session, I think this might be the one to do it. I'll go ahead and